Should I?
Okay.
Yeah.
You ready?
Can you hear me?
Yes, clearly.
Yes. Okay. Okay.
Okay.
Great. Yeah.
Thank you.
Thank
Okay.
you.
Okay. Then we have now around almost 40 participants in this webinar. Then it's time to opening the IEEE-PES webinar on the topic diagnostic on motor and generators. So the speaker you see in the screen is Mrs. Khushbu Thakur. Do I pronounce your name correctly? Yeah.
Yes.
Okay. She received her master degree in electrical engineering with specialization in condition monitoring of electrical apparatus. She is now working with Omicron Hong Kong as regional application specialist with more than 9 years of experiences in diagnostic testing of high voltage electrical assets. She is now also an active member of Omicron Academy to facilitate technical training. Before joining Omicron, she worked with Reliance Industries Limited in India. So the topic today, we're talking about the diagnostic of rotating machine. As we see, the rotating machine is an important element in power plant and also industrial applications. So the content in this webinar, so the speaker will discuss about various offline testing and also in-service tests, and then followed by diagnostic techniques, interpretation of the result, and also share her experiences of best practice. If you're ready, you can start now. Thank you.
Thank you. Thank you for the introduction. And let me share my screen. Just a moment. I hope you can see my presentation now. Yeah. Can you see my presentation now?
Yes.
Yeah. Okay. Okay. Great. Welcome to this webinar on diagnostics of motor and generators. And the whole idea for this is because this is a short session, so we are trying to cover everything within 1 hour, which will also include some Q&A section. So the idea behind this particular webinar is to try to cover at least the major testing techniques that can be utilized in field, and try to talk about different as much as possible within this time duration. So what we will be talking about today in agenda, because my introduction is already done, so what we will be talking about is we will be talking about the failure statistics, and then going into the test overview directly. So we will directly jump into the interesting technical topics, and then we will talk about a little bit about the asset construction, and finally, we will go into the individual tests, so some installation tests and other specific tests. I've not included all the tests here because of the time constraint, of course, but if you have any queries, you can get back to us anytime. So if we talk about statistics, now there are two different categories here. One is generators and motors. So in generators also, you will see hydro generators being treated a bit differently because of the application, and turbo generators a little bit differently. However, what I tried to do was try to find out several different surveys that have been done. I think there was a survey done in 1980s by EPRI, and then in 1995 by IEEE. So there are several surveys done. This one is from SIGRE as well. And in all of them, you will see that in case of generators, actually insulation damage is one of the most prominent criterias for failure. So one of the most common root causes, like in SIGRE, you see 50% incidents were caused by because of insulation damage. In case of IEEE, this particular paper that we refer to, 56% are caused by insulation damage. So it gives us an idea that where should our focus go into the testing. And because today we will be covering more electrical concept of it, so we would focus our energy more on the insulation side. Now, also looking at the insulation, what's the breakup by itself? Again, aging, contamination of winding, and internal partial discharges are some of the major contributors. The percentages can vary, but these are some of the major contributors that are contributing to your insulation damage. So that gives us an idea of where our focus should be. For high voltage motors, there is a similar picture, a little bit different because in many cases, what I saw was that mechanical breakage is more dominant. But then in mechanical breakage, the bearing fault is also included. So if we talk about bearing fault, or if we remove the bearing fault, then again, insulation is one of the key criteria or key root causes that has to be focused on. So what you can see from here is electrical tests can discover problem. It's not magic, so it's not going to tell you before the problem has arisen, but it will tell you in a very initial condition if you know what to look for. So it can discover these problems before they become extremely critical. So in a rotating machine, I mean, this is true for all your electrical assets. In reliability study, whenever you study reliability of different electrical machines, one very common criteria that people read about is the bathtub curve. It was taken from insurance companies. For human beings, what's the life cycle criteria? And the same has been applied to the electrical industry as well. So you can see this bathtub curve, and right now here, what I've included, let me just use my pointer. So here, what I've included, I've not included the initial, what we call infant mortality rate or the early failure rate, but you can see an inverted bathtub here. So what is the expectation from any electrical asset, and in this case, rotating machine, is that you have an initial period where there will be some high faults because of maybe design failure or some manufacturing defects. So that's called the infant mortality rate. Then during the service life, there will be a fairly constant failure rate. And when I say fairly constant, it doesn't mean that it's just stable. There can be some random faults. Like, for example, I had a failure where a worm entered into the switchgear. So that's a very random fault. And that is very much dependent on the maintenance. So you cannot say that that increases your fault rate, because that's something that we could have done or we could have avoided. So there is a random failure rate, but it's fairly constant. And then again, the aging factor comes into place. So what I want to emphasize here is in the aging factor, during the life, there are several negative influences. So you have thermal stress, you have electrical stress, you have ambient stress, and you have mechanical stress. So all these negative influences will try to reduce your life. And what can be done is, and what people are doing already, it's not as if this is a new concept, but what can be done is you can make your testing and corrective measures in a more planned way, in the sense that you have major overhauling periods. Some tests can be done only then. You have some limited inspection periods. So in that scenario, you can actually conduct only certain number of tests because in some tests, you need the rotor out. So careful planning of all your test requirements, and then subsequently getting immediate results so that something can be done. So let's say you identify a problem during a major overhaul, and if you have to wait for analysis, then you might not be able to correct it. So I'll share a case where we found a problem in a generator, and then immediately the testing was done. This was actually in a core. There was a fault. Immediately the fault was found, and we didn't need days to do the analysis, because in my previous company we were doing this, and we did analysis internally. So we did analysis, we found the problem, and then immediately the OEM was on site because of the major overhaul. So OEM addressed the issue. He basically did the on-site maintenance, or on-site repair, I should say, and rectified the fault. So it can be done, and therefore the life can be improved by this. So if we talk about how the surface life is for your machine, you have these initial, factory. So if you want to avoid these teething problems, like the infant mortality rate, if you want to avoid that, the concept comes much before that. So you should know what factory tests are being performed. You should, because utilities specify these factory tests. There is no hard and fast rule as to what tests are to be conducted. Yes, some tests are mandatory, but then not all tests are mandatory. So it has to be your choice that you specify these tests are mandatory for my particular machine. And once you have these factory results, they are like your fingerprint. And most tests, most assessment tests for insulation, for other characteristics, are fingerprint tests. So if you don't have the reference data, then it might be really difficult for you to do an analysis. So you should, in the service life, you have factory test, then you have commissioning test. Again, this is a reference result. And these two can vary because of the characteristics, because of the situation of the field. These two results can vary. And this is your final fingerprint test. So your commissioning test is your final fingerprint test. And then in the service life, you can go for these two plans, so to say, and which one to choose depends on what is the criticality of the machine. So let's say this machine is really critical, then you can go for continuous monitoring. Not everything can be monitored continuously. You have temperature monitoring, you have vibration monitoring, you have partial discharge monitoring. So there are some continuous monitoring available. You can go for that for extreme critical machine. And if it is not so critical, then these days there are also temporary monitoring concepts quite, they're becoming quite stable. So to prevent initial failure, between, let's say, 1 to 5 years of your initial period, you can have a temporary monitoring installed on a periodic basis, and then you can plan your offline tests or temporary monitoring in the service life. And the periods can be varied. Maybe when you are sure, okay, I have reliable operation of my generator or motor, then you can have a longer period, and you can shorten the period as you go towards the aging. So it's very much, I know there will still be some time-based maintenance, like bearing and like gaskets, those kind of things. There will be time-based maintenance, but some maintenance you can have on periodic basis in this particular scenario. So this actually really helps you in identifying where your focus should be, which offline tests you should conduct when. Maybe some tests only need like major overhauling. You cannot do anything about it without the major overhauling. And we'll come to that a little later. So when we talk about tests overview, we have offline tests, we have online tests, And online tests can be continuous or temporary monitoring. And there are wide variety of tests, which we will go to individually. And you can refer to this table for that. I just tried to jot down some failure criteria or failure modes for individual parts of your machine. This is not all-inclusive. If there are hundreds of failure modes available, and I've tried to pick up some major ones here. So you can see your state of winding, partial discharge, contamination, aging, insulation integrity, interturn faults, connection problems. You also have faults like your slot wedges are loose, your core has shorted laminations or overheating. Maybe in your rotor, you have interturn fault. And of course, bearing is one kind of fault. And if you refer to the tests, one common usage, I think this goes in the inspection as well. And this is visual inspection. We also called it look, listen, feel. So, okay. So we also call it, we called it in field LLF, or look, listen, feel. And the idea was that, you know, there are these experienced people in field, and really experienced, like 20 years they are doing it, and they can just tell by the sound or by touching that whether there is very high vibration. I mean, I found it quite interesting that they could tell that, and it's actually a pretty good criteria if you have experience and if you know what to look for. Um, However, not everyone is experienced. Everyone starts at some point. So there are other tests that are to be conducted. So for insulation, today I would be focusing on some specific tests that we will talk about. So capacitance and dissipation factor is one common insulation test. Then we talk about partial discharge as well. Um, and for core, we will talk about the electromagnetic core imperfection measurement. I will also briefly cover the DC winding resistance and pole impedance, and maybe a little bit about IR, but IR is one of the most common tests, so no need to go into too much detail. Okay, so before we dive into the insulation tests, let's understand the construction of the insulation. So this is your stator winding. And if we look inside, this whole thing is your core. And then you have these slots in between where the winding is inserted. So you have these single windings. Like for example, in this slot, there are two windings placed, and they will be connected either in lap connection or wave connection. You have the slot wedge here. There are air ducts for cooling, and internally, if we see the construction, the insulation construction, again, this is the core. So you can see in the slot there are two windings, and one is constructed of, so let's say these are your individual strands, and all strands are isolated from each other. So there's an insulation around this strand, and then over it, you can see here there are markings. So over it there is inner potential grading, and over it there is main insulation, you know, mica tape layers, and then all along this slot, there will be outer corona protection. And the idea behind having outer corona protection is, I mean, every insulation in the layers that I talked about, every insulation has a purpose. So outer corona protection, let's say you have the core. So you have these laminations of the core. They cannot be exactly of the same height. So maybe one is a little bit heighted than the other. And because of that, there will be non-uniform electric field across the whole slot. So you need an outer corona protection so that this can be uniformly distributed. The field can be uniformly distributed, and you don't have discharges. because of that. Also in the end winding portion, then you have end potential grading, and this is to ensure like you have a uniform potential change across the end winding. You have these wedges and spacers connected in the end winding. And finally, yeah, you have the core, which is made of different laminations. So you can see here the core. It's not one solid, I mean, this we are taught in college, right? So it's not one solid part. It's made of several uh, pieces, several layers, which have insulation between them. So they are laminated sheets, and that is, of course, to reduce the hysteresis and eddy current losses. What can happen is they can get shorted, and that's where we will come in with another test we will cover in later slides. Okay, so insulation tests. IR and PI. I think one of the most common tests in the industry, insulation resistance and polarization index. And yeah, just wanted to show you which capacitance we are checking. And you can see the definition. I'm not going to read the definition by itself, but what we are trying to find out, we are giving a DC voltage and we are trying to find out the resistance of the insulation. Normally for IR, the measurement is done for 1 minute. And then when you do PI, you do for 1 minute, you do for 10 minutes, and it's a ratio. IEEE does give you a criteria, like what is the different criteria for different thermal class rating. Uh, but please remember that IR is treating the whole insulation as one big bulk. So if there are individual hotspots or if there are individual faults happening in your stator winding or core, I mean different insulations, then you won't be able to see that with IR if rest of the insulation is healthy. So it treats the whole thing as a bulk. You are basically testing as one bulk of insulation. So it's a very good tool, but it is not giving you a complete picture. It is giving you some picture. Use it as a reference, but don't use it as the only criteria. So the next test that we come to is the capacitance and dissipation factor. And yeah, I mean, I won't go into the theory of this. Yes, we are treating the model as R and C parallel circuit. And what I would like to show here is there are two results that are extremely important from capacitance and dissipation factor measurement. So capacitance definitely is one value that you're getting. And if the capacitance changes, that means there's some change in the geometry. But from the dissipation factor perspective, 50 hertz just gives you one value. Yes, you can compare between phases. And like in this case, you can see for phase 3, the dissipation factor is relatively high as compared to the other two phases. So this is a trending criteria. So you need to do a trending in order to know if your insulation is deteriorating, and there is no hard pass-fail criteria to it. So no one can say, okay, I mean, it's not as in power transformer. There's no hard pass-fail criteria in here. Even for power transformer in service, they don't give you anything. So in service, it's always a challenge. So next thing that I would, and what standard also recommends, and we have found in field, it makes absolute sense, is the voltage tip-up test. When you're doing voltage tip-up test, so as you can see here in your, this is from the IEC standard, and you can see IEC says, do the test at 0.2 times your rated voltage, 0.4 times your rated voltage. So keep on increasing by 0.2 times, and then it gives you a table where it tells you, okay, if your delta tan delta is within this range, it's good. They give you three criteria. Like one is tan delta at 0.2 times, one is the delta tan delta, so this change, and one also is the tan delta at 0.6 and tan delta at 0.4, I believe. So they give you these criteria. These criteria, however, are for single windings. So again, there are no absolute criteria for an in-service whole stator winding. For single windings, when they are being tested like a single coil, then there are some criteria to it. But for the whole winding, there is no pass-fail like standard value. This is okay, this is not okay. It's not like that. So what I would say is this gives you a really good picture. So maybe just seeing this, you might not be able to tell, but seeing a good machine should, when we are going up in voltage and when we are going down in voltage, there shouldn't be a variation. And another thing is when we are going up in voltage, the increase shouldn't be too high. If with change in voltage and with increase in voltage, your tan delta is increasing a lot, that means this is an indication that there is PD inside your insulation. Because PD is triggered by high voltage, there will be some inception voltage for PD. And then beyond that inception voltage, the PD will start to happen. So this, I mean, comparing the two machines, I can tell that this one may have high PD, this one may have low PD. Again, it's just high and low. It's not, it's not as if, okay, this is going to fail maybe in 1 year time. So this needs further investigation. That's the idea. Okay, so because we talked about PD now, how to do the test. Again, this is taken from 6270, IEC 6270 standard. You have your source, you have the blocking impedance for blocking any PD coming from the source, and you have your test object, coupling capacitor, and finally the measurement system. So measurement system consists of the coupling device, the data acquisition unit, and the control unit, which basically talks to your laptop and transfers the data. So this circuit is for offline, but it's also valid for online. The only thing is you won't have a blocking impedance because you cannot really put a blocking impedance in your online circuit. And you will not be able to do like a voltage tip up or a step, increasing the voltage in steps and finding out the inception voltage. So you won't be able to do that in online. However, if you can connect in online condition, a coupling capacitor permanently connected there and then do the measurement. So let me show you how it would look like. Yeah, this one is for offline again. So let me show you first online. Okay, so this is, let's say this is your rotating machine. You can put permanently install these 3 coupling capacitors. Again, this terminal box is optional. If you're using continuous monitoring, you can just put a data acquisition unit here. And if you want to use like temporary monitoring like shown here, so in that case, you would put this terminal box. There are safety measures inside it so that it doesn't remain open at any point of time, the terminals. And then while your generator or motor is running, you can do the measurement at any point of time. You can even use the offline devices to do a spot measurement. You can use devices to, like this device actually has a storage, internal PC inside it. So you can use these kind of devices to store the data for a short period of time. It can be 1 month, 2 months, so leave it for temporary monitoring. And this helps you to identify whether you should go for continuous monitoring for this device. So yeah. Again, coming back to this, what I wanted to show you was that when you're doing partial discharge, so for offline measurement, like let's say you have a shutdown and you want to do capacitance and dissipation factor measurement, you're using this kind of device. You know, this is from Omicron TD, but you are using this kind of device as a source. You need compensating reactor because the capacitance is high. If your capacitance is not too high, you might not need it. So that's a story for another day, but you are using this kind of source to do a tan delta measurement. Just by adding some device like coupling capacitor and the measurement unit, you can now do a PD along with, so no change in setup, but you're getting more information out of it. Uh, I wouldn't say no change in setup, but a little bit change in setup. You just add a coupling capacitor and some measurement device, and you're able to get more information out of the same setup almost. So now what I wanted to show you is, let's say I've done the measurement. The biggest challenge with PD is not the measurement itself. Connection is pretty straightforward, and the problem comes when you have to do the analysis. So let's say I get a result like this. What is it? I mean, if someone shares this, yes, I've got something like 1.5 nano and 1.4 nanocoulomb, but I don't know what this is. So now, I mean, this is not a new characteristic. There are features like automatic cluster separation now in picture. So you have these different clusters, and what we do normally is we take measurement from the 3 phases and then plot it on the 3-phase diagram and try to find out the vector summation of that particular type of PD and a signal. So here you can see this cluster corresponds to this, and there is, I mean, AI is pretty powerful these days, right? So you can also get like automatic pattern recognition. And here I can say, okay, this is not AI, but this is just my calculation, but you will also see this in AI. So this one corresponds to ambient noise. Sorry. Yeah, this one corresponds to delamination, and this is high risk. This is I mean, you can refer to IEEE guide for this. And this one is, it looks like an N-winding surface discharge and medium risk. And this one is a combination of microvoids and maybe a little bit of N-winding discharge, so low to medium risk. So here you can see now very clearly that there is some pattern which indicates delamination, and it is of high risk. Just from seeing the first picture, you wouldn't be able to tell that. So I mean, this I took, you know, it's very similar to what is given in IEEE, and you can see different different patterns. In case of rotating machines, it's pretty good. Actually, the database is pretty well established. So you see all these different patterns, and different patterns actually indicate. So in this case, we could see that this is how the pattern looked like, and you can see delamination is definitely one of the highest risk. Okay, so now I go to use case, and we'll come back to the partial discharge patterns in the use case. So this is my first use case. This is a hydro generator, 6.4 kV, and the rotor was pulled for a bigger maintenance. And you know, when you are doing a standard maintenance, you do certain tests for diagnosis. So insulation resistance, dissipation factor, voltage withstand, and partial discharge. And actually, you can combine all these 3 tests. You can use the same source for doing dissipation factor, voltage withstand, and partial discharge measurement. So in this case, you can see this is phase U with V and W grounded. This is phase V. And once plotted together, you can see very clearly that phase U had significantly higher values as compared to V and W. So what was decided was, let's go for the voltage withstand. And they were supposed to do, I mean, for voltage withstand test, again, uh, it can be mutually decided between the manufacturer and the user. For an in-service generator, you have to go up to watt voltage. So in this case, they decided to go up to 1.2 times the rated voltage, and the breakdown happened at rated voltage. So what they decided, actually, why they decided for voltage withstand is basically, if it's going to fail, it should fail today and not later. Because if it fails today, I can do something about it. If it fails later, I don't know what to do. And actually it failed. So there was no additional standstill time. The maintenance could be done, repair could be done immediately. And that was, I mean, that basically avoided a bigger damage that would have happened if it was in service. Another use case, this is a 14 MVA 10.5 kV motor, so pretty huge. Here you can see the insulation resistance measurement was done, PI measurement was done. So this is from factory results. And then the measurement was also conducted, I mean, this is around 8 years later. And you can see the insulation resistance is I mean, this is not 10 minutes, actually, this one is 1 minute. But PI, you can see there is quite a bit of difference from phase V to phase W. Please remember that the results are still within limits. So it's not as if the results have crossed the limits, but the only thing is you can see a significant lower value in phase W. So however, this don't give you any indication of what is the degradation. So as I said, it treats the whole insulation as one bulk. It was decided to go for the capacitance dissipation factor and partial discharge measurement. And as you can see here, we used the same source to do capacitance dissipation factor and then partial discharge using the partial discharge measurement system. And actually, in this case, they couldn't go above 70% of the rated voltage, because beyond that, they started to get horribly high, like crazy high partial discharge value, something around 500 nanocoulomb. And you can also see the delta tan delta characteristic, which has a very this looks like a hysteresis curve, right? So it has a very big hysteresis loop, I would say. It's not actually a hysteresis loop, but just looks like that. So they didn't want to go above that. They didn't want to go above that because there was a risk of breakdown. So here you can see the inception voltage started at 40% of rated voltage, and at 70% they had something like 500 nanocoulomb at 8 kV. At 7 kV it was around 100 nanocoulomb. So it was decided, okay, let's see the pattern, what exactly the pattern indicates. And pattern indicated that there is a PD between the outer corona protection and stator slots. So as I said, you have these stator slots at the bottom, and they cannot be 100% uniform. So you have this outer corona protection, which is trying to make the field uniform. And this actually indicates that this is, the most common failure for outer corona protection is there can be mechanical abrasion on it. So this actually indicated that there is a PD there. And it also indicated maybe there is PD in the end winding area, in the end winding potential grading. So this was brought back to the workshop. Now, the first thing that you notice is it's heavy on contamination. So end winding definitely can be one of the culprits, because the end winding would be most exposed to this kind of contamination. And you can see here, I mean, it's really, all the end winding portion has pretty high surface contamination. And there are defects at OCP and EPG both. So now this is a question of chicken and egg. You never know which happened first, which started it. Maybe the contamination started it, and eventually it started to destroy your OCP as well. So because of this high discharge, maybe in the end winding area, it started to have very aggressive ozone and then reaction at the metallic surfaces. But it's a situation of chicken and egg. You don't know what happened first. So maybe OCP happened first, and then the end winding started to degrade. So moving on, we are going to talk about some other specific tests. I will just briefly cover them because we don't have too much time. So uh, we'll talk about the DC winding resistance measurement. Uh, it can be done in both stator winding and rotor winding, or I mean, in some case you have these poles. So um, basically, what you can detect from here is, in case of stator windings, you can detect something like bad soldering. And in case of rotor, bad contacts. So like in this example, if you see, sorry. Yeah. In this example, if you see the winding resistance is measured for the stator winding and at 50 ampere. So you can see this particular phase has higher value. And what was done was, a 250 ampere was injected, and with a thermographic camera, this was tried to see, okay, what is the problem with my stator? And you can see here, this has something like 41 degree. So your 41 degree is, I mean, there are some hotspots at certain portions where actually the joints are, and you can see the kind of damage it can cause if you have bad soldering. So this is one example of what you can detect from the winding resistance measurement for stator winding. Going to the pole impedance measurement. So this also is for rotor. If you have interturn faults, this is a good test to detect it. And what we do actually in this is we energize it by giving a voltage, and then try to measure the voltage at each pole so that you get something like, so you energize it by giving a current and then try to measure the voltage. So what you try to measure is the impedance, and the idea is that you plot it for different poles, and it should remain within this plus minus 2.5%. It's a kind of rule of thumb. It's not exactly any standard, but it's more like a rule of thumb that you follow. This particular variation should be within plus minus 2.5%. So in this case, you can see this is for a 44 pole machine, and for a new machine there is only one variation a little bit. But for an old machine, you can see quite a high variation in very close to the last few poles. So as I said, there are no standard limits. This can be used as rule of thumb that this value should remain between plus minus 2.5%. One more test that is, it's again, it's a new application of an existing test. So FRA has been, SFRA has been a very common test for power transformer. But I actually read some papers where people have started to use this in rotating machine, and it actually, if you have any geometrical, deviation, any deviation in the capacitance or in the inductance of your or resistance of your winding, then you would be able to see that with SFRS, specifically if your rotor is inside. So any variation between the, so this test doesn't exactly need for you to remove the rotor. Your rotor is still in place, and then you perform this measurement. Then you will be able to know, okay, I have a certain kind of resistance, inductance, and capacitance circuit. And there will be some resonance point because of that. And then if you have some variation in your circuit due to some fault, maybe due to some distortions, then you will be able to identify that. So again, this is a fingerprint test, and there are very promising results with SFRA. Now we come to the last test that we will talk about today. That's the electromagnetic imperfection testing, and this is to identify any fault in core, specifically if you have shorted laminations, overheating. And you know, if you have core fault, one common test is core flux test. In that, what you do is you energize your stator at rated flux. So you give it rated flux, and then with a thermographic imaging camera, you look at the whole periphery of the winding to see where you have hot spots. And the problem, I would say, is the safety, because you are energizing it at rated flux, and then you have to go near it to see it through a thermographic imaging camera. It's not really safe. And the other problem with that is because you need rated flux, you need a very big source in order to energize it. So I remember we did it in field, and we needed another transformer to really like have a generator, have a transformer, and then give it voltage. So you need a big source for that. And so just to avoid this test, complementary test, I should say, or you can use this instead of that, is the electromagnetic imperfection testing. It's not a new test, but I just wanted to briefly cover it. So you need to excite your core. In this case, only up to 4% of rated flux, so a very nominal flux value. And then you can use a pretty portable source in that case. And the idea is that if you have these shorted laminations, there will be current induced in the damage, and there will be some flux produced because of that. So you use a coil. You basically run that coil across your slots, and if there are some currents like this induced, they will be picked up by this coil, and you can have a plot to see, okay, where exactly I'm getting different values. So this is how our setup looks like. We have the source, we call it CPC 100. It's like a multifunctional test kit. And then we use something like, it's like a semi-automatic, so use a rail, and then this Chatok coil runs over that rail, and you can basically cover the whole periphery with this. So you can see the excitation cable, and then you have this. So the use case for this, the use case for this is what we did. This generator came to the workshop, and they had a big fault, so they had to replace core and some winding portions. So what could be done was we created some faults in it, and then tried to measure that with the electromagnetic flux test, electromagnetic imperfection test, and also with core flux test. So you can see these 2 points from the electromagnetic imperfection measurement, and the same could be measured from the core flux test. So it actually gives you like similar results, but with much more safer and much more smaller portable solution. So yeah, I think that covers my presentation for today. Thank you, and I hope I'm on time, maybe a little bit beyond that, but yeah. So you can ask your questions, please. Let me see.
Yes, if any participant for this topic have the question, you can ask the speaker to this room. So maybe I start the first one. When we're talking about the bathtub curve, right, at the beginning of the presentation, um, I would like to ask some like, are there any cases that the rotating machine fail in the infant mortality or in the beginning of the lifetime? In your experience, is it a lot or it's just a few?
In my experience, not a lot. I mean, mostly what I found was aging period was the
Mm-hmm.
most common cause of failure. Maybe a few, and that's very much related to the manufacturer itself. Like
Yeah.
one particular manufacturer had a higher infant mortality rate. I don't
Mm-hmm.
want to name it, but it's
Mm-hmm.
like, yeah, that was the case. But I haven't seen it like over the whole range having a very high infant mortality rate because
Mm-hmm.
micro insulation is pretty good in that scenario. Yeah.
Yeah, right. Because I think so that the infant mortality rate should be low, right? Because of the quality of the manufacturer, except some manufacturer. And the other thing is the expected lifetime for the generator. In your experience, how many years that the generator, for example, in the power plant has been used, like more than 40 years, have you seen, or less than that?
I have seen up to 40 years. Yes. After
Mm-hmm.
40 years, like I had a case where it actually the core, the one portion of the core basically melted completely
Mm-hmm.
after 40 years. So um, yeah, it's like and there is a lack of information as well. So maybe that could have been avoided if we did certain tests on a routine basis. At least as far as I understand, I think we could have avoided that if we did some tests in offline condition on a routine basis. Like we used to do, regular tan delta and
Mm-hmm.
IR. That's the only test that we used to do. And then the equipment definitely after 40 years, still 40 years it gave, but then after 40 years it did fail. Yeah, so
Yeah,
I
right.
believe that's the case. In most in service I've seen 30, 40 years, at least old generators. New generators we don't know as of now, but yeah, old generators.
Right. And that is the point, because when the generator get older, and then the withstand voltage test maybe cannot raise up to 1.2 times of the rated voltage, right? It's maybe uh, a dangerous situation that can break the insulation, especially for the old generator.
Yeah. As I said, in that particular case, it was decided that if it is going to fail, let it fail now,
Yeah, right.
because we can do something. And this was decided between the manufacturer and the user. Already, manufacturer doesn't have any warranty in that duration.
Mm,
It's already quite aged. So uh, it was decided that to go for that. Definitely for voltage withstand test, the the standard only gives you criterias for factory, and then in service,
mm-hmm,
it tells you okay, you can reduce it. To how
mm,
much, that is definitely up to speculation. Like in many cases, people don't even go to rated
mm,
for the voltage withstand test.
right. So I think we have one audience would like to ask you a question, right? So,
Yes, let me read that. So
mhm,
for PD sensor, what is the capacitance, coupling capacitor to be used? It depends. I mean, uh, we cannot really go up to the capacitance. So ideally, as per standard, you should have a coupling capacitor capacitance which is higher than your test object capacitance. Practically, not possible in case of rotating machine because in rotating machine, your capacitance is something maybe some hundreds nanofarad or
mm,
microfarad. So in case of that coupling capacitor, what we normally use is like 2 nanofarad. And in IEEE, there is a curve depicting if you use certain kind of a certain rating of coupling capacitor with respect to the test object capacitance, so CK by CT, I would say, there is a curve, and it gives you a sensitivity idea that if you're going to use a certain range, then what would be the PD measurement sensitivity for that? So you can refer to that for the information, yeah. Do we need the database to analyze the PD pattern? Actually, as my colleague, Hinson replied, yes, we now have automatic pattern classification. Definitely, there's a good database, as I said, for rotating machine. There is a good database, and you can use that. You remember the slide that I showed with all patterns, so you can use that as reference. What the automatic pattern classification does is it tries to calculate the probability. So what we as humans do, we see a pattern, and then how we analyze it is basically we try to compare it with our existing pattern and see, okay, maybe there's a little bit of deviation. So let me show you. I don't think you can see my slide. Just a moment. Let me show you the slide again. And yeah, I wanted to refer to a particular slide. So we go back. This one, as you can see, this is a comprehensive list. And you can see here why this says that it is a combination of the two. If I, as a human being, if this is given to me and how I would analyze it, I would see, okay, there is something like microvoid patterns, and then there is something extra here. So you can see some extra pattern here. The AI is actually doing the same thing. So it'll calculate the probability of different patterns, and it will see, okay, I have maybe 80% probability of it being a void, and then there are some probability that there is n-winding discharge as well. So we have now this pattern classification, which really helps in giving you an idea. Please remember that this does not displace the human beings. Human beings still will be there. You are the decision maker. So if you get some result out of the pattern classification, you have to use your own discretion. So it doesn't replace you. It's just giving you an idea as to which direction to look for, and try to find out whether you can resolve the issue. Okay, so I think the next one is, have you ever considered the pattern of frequency dependence on tan delta with specific case? Yes, and this is more, I don't know if you have seen this in rotating machine. I haven't too much. Actually, in other type of machines, that is pretty common. But in case of mica insulation, actually, I haven't seen too much influence. If you have any specific case, do let us know. I haven't seen in mica insulation too much influence from the frequency perspective, so frequency dependence. Okay, so is database provided with PD system with no additional cost and free for future update? You have to buy it. It's a license, so you have to buy it, and then it's no future cost. Yes. What would be the comparison between measured by coupling capacitor and radiation at RTD method for PD measurement? Um, By RTD, I assume you are referring to the temperature sensor. Is that it? So see, the coupling capacitor is the standard method. You are actually measuring an electromagnetic signal from using the coupling capacitor. In any other method, I mean, don't know if I'm understanding you correctly, but if you're referring to the RTD, the temperature sensors, the problem with that is it is telling you values of specific points. So it again, it doesn't give you a complete picture in the sense uh, two different patterns, totally two different criterias, and definitely coupling capacitor is the electromagnetic signal capture. So that's actually measuring the exact value that you're getting. So it gives you amount of PD, it gives you the intensity, it gives you, it looks into if you are using like a 2 nanofarad, so it actually looks into the you know, more than 50% of your winding. So it looks into quite a bit of your winding. So it very, very different methods, I would say. Yeah. Can we use the PD pattern database to analyze the aging of generator? They are correlated, aging and PD, but I wouldn't say you can tell just from PD that whether it's aging or not, because there are other, so PD just gives you identification that inside your insulation, whether there's a discharge happening. But if you have other kind of faults and like, for example, if your contact is not proper, I showed you an example of contact resistance, right? So if your contact is not proper, you have overheating, like local overheating, you have local hotspot, that would not be detected by PD. So aging also causes this kind of local hotspots. If you have core problems, then you have to go for core test. So some tests are complementary to each other. Aging gives you one aspect of, PD gives you one aspect of aging. That is due to aging of your insulation, there might be discharges starting to happen inside your insulation. But any contact problems or any core problems cannot be detected. Local hotspots cannot be detected by that. From your experience, which part of the machine has the highest hotspot and how much temperature? This is a relatively difficult question because it can be end winding, it can be core part. I don't think I have seen too much on the star side, you know, because there's relatively no voltage there, or very low voltage if you move away from the star point. But core, definitely. End winding, yes. I have seen, you know, the distances sometimes during the manufacturing. And this makes me come back to the first question that that was asked. You know, infant mortality rate. Some particular problems you will not be able to identify, even if they are manufacturing defects during the infant mortality time period, because they will start to develop and they would have some problems in the future. So that one such example is the gap between the end windings. So if, let's say, the gap is not uniform all over the periphery of your stator. So in that case, eventually the insulation at that point will start to deteriorate. So that's also one point. Actually, in one generator, I saw that it was sparking. So it was not even partial discharge. It was like total discharge. It was sparking, and that will not be picked up by PD. That you can pick up just by giving a voltage, and you will see, you will actually look at and hear the sound very clearly. So, okay, I think we'll come back to the next question. So, is the PD pattern depend on a machine MVA? Not so much. It actually very much depends on the voltage and how the insulation is rated. MVA definitely determines that what kind of insulations have been used, and thermal rating determines that as well, how much current it's going to carry, but not directly, no. we have an interesting question. What is the difference between the coupling capacitor, 80 picofarad, and 1 nanofarad? So again, I refer to the same IEEE standard or guide, you can say. There is a curve in that which tells you PD sensitivity based on CK by CT or C test object capacitance. The thing is, I actually like, I don't know how much time we have, but I really like to give an example of a bottle and a glass. So when you're doing PD measurement, your bottle is your coupling capacitor and your glass is being refilled. There is a deficiency, there is a PD, so there's a deficiency of charge in your machine insulation, and then the coupling capacitor is trying to refill that deficiency. Let's say this deficiency is higher. Then if the coupling capacitor capacity is lower, it might not be able to refill this requirement. And that's where this comes in. So if you use 80 picofarad, you will be able to look into, let's say 10 to 15% of your machine. So from the terminal up to 10 to 15% maybe. And if you use 1 nanofarad or 2 nanofarad, you'll be able to look into the machine a little bit more in depth. So you will have higher PD sensitivity. It's very much dependent on that. So yeah, I hope that answers your question. So the next one, if the PD in slot found, how do you illuminate? How do you illuminate it? I'm not sure I got your question.
Or I don't clearly understand as well, but maybe he means that how to locate the location or where in the slot. I'm not sure. Right?
Yeah, I mean, what I can tell is, again, referring to the overall chart for the insulate. I mean, just I think. Let me share. Okay. So again, referring to the overall chart, the whole table that I showed, there are some specific pattern for slot type discharge. So if you see a slot discharge, there is a specific pattern that actually indicates a slot discharge. And please remember that slot discharge is actually happening. So you have the slot, you have the maybe 2 binding layers, and then internally maybe something is happening. So you will be able to identify that. How to rectify it, the only way is you have to take out the winding. So repairing it on site is possible. What OEMs do is they cut the existing winding, take out, identify the fault, in which winding is it happening? Is it in the first winding? And this also you can find from your layers, because let's say you have a fault in certain phase, then you will be able to identify, okay, let me look at where exactly is it happening. So you have to cut the existing winding, lay the new winding, and then do you know, I think welding is called, or soldering basically. So you do the soldering on. I mean, this can be done on site, and the manufacturers or the repairers do it all the time. How to reference the testing result if your stator is internal star connection, the tan delta tip-up test. Okay. I understand the problem. Yeah. You don't have individual phases to compare the results. The only way is to have trending. There is no other way to do it. Yes, you can do measurement for 3 phases, but still the 3 phases are shorted on the other end. So you can still use them for comparison. You can still see if your delta tan delta is too high. And as I said, in standard, the delta tan delta is given for individual windings, but you can still use it as reference and decide your own delta tan delta, what is acceptable limits and what needs further investigation, and then do a trending. That's for any of these tests, actually trending is one of the best too. So I think that's about answers it. Thank you for inviting us. Yeah.
Yeah. Yeah, it's a lot of questions. I think this topic is very interesting for us. And thank you very much, the speaker, Mrs. Khushbu Thakur, for spending your time and your effort for this topic with us. And we enjoyed very much. And also thank you, the IEEE-PES Thailand, for organizing this webinar, and also the participant for joining us today, and hope to see you again next time. Thank you very much. And goodbye.
Thank you. Thank you. Bye-bye.
Goodbye.